What if you need to track workflow state between steps, but don't want to implement full database persistence yet? You'll see LangGraph's basic checkpointing structure using in-memory storage, where we wrap API calls and tasks to demonstrate the pattern for state isolation. The example shows the foundational approach with thread IDs and task decorators, while clearly distinguishing what's needed for true durability versus this simplified demonstration.
From typing import not required. From typing extensions, import type dict. Import UID. From LangGraph, checkpoint, memory import in-memory saver. From LangGraph, func import task. From LangGraph, graph import state graph start end. Import requests. Hash define a typed dict to represent the state. Class state type dict. URLs, list SDR. Result, not required list SDR. At task. Def make request URL, SDR. And make a request. Return requests, get URL text, 100. Def call API state. Example node, that makes an API request. Requests equals make request URL for URL in state URLs. Results equals request, result for request in requests. Return. Results. Hash create a state graph builder and add a node for the call API function. Builder equals state graph state. Builder, add node call API. Hash connect the start and end nodes to the call API node. Builder add edge start, call API. Builder, add edge call API end. Hash specify a checkpointer. Checkpointer equals in-memory saver. Hash compile the graph with the checkpointer. Graph equals builder. Compile checkpointer equals checkpointer. Hash define a config with a thread ID. Threaded equals UUID. UUID 4. Config, configurable. Threaded. Hash invoke the graph. Graph invoke URLs. https://www.example.com config.
This demonstrates the task decorator pattern in LangGraph for structuring workflows with checkpointable operations. The example shows how to wrap external API calls in task-decorated functions while maintaining a simple state graph structure, with thread identifiers providing execution isolation. Unlike production implementations, this uses in-memory storage solely to illustrate the pattern's basic structure. The approach works by explicitly marking side effect operations with the @task decorator, which enables their results to be recorded at specific checkpoints. The sequential request pattern despite list comprehension shows how to maintain execution order while still benefiting from checkpointing, though actual resumption would require both persistent storage and explicit thread identifier reuse. The state schema intentionally uses a simplified structure common in examples, focusing on demonstrating the decorator pattern rather than production-ready state management. This pattern serves as a structural template for building checkpointable workflows, with the official documentation showing similar examples that prioritize pattern clarity over complete durability. The in-memory storage demonstrates the basic mechanism, but doesn't provide actual persistence across restarts, while the task decorator shows the required pattern for making operations checkpointable when combined with proper thread management. The example's primary value lies in illustrating the decorator pattern's role in workflow structuring, rather than implementing complete durable execution. Let's break it down.
From typing import not required. From typing extensions, import type dict.
Imports typed dict for defining the state schema structure and not required to mark fields that may appear during execution, but aren't required initially. This matches the pattern shown in LangGraph's official documentation, where example state schemas often declare potential output fields up front, even when they're populated later. The combination enables type-checked state management while accommodating workflows where certain fields only exist at specific stages. A common pattern in graph-based execution where nodes dynamically add data to the state.
Import requests.
Imports the requests library to enable HTTP GET operations. This provides the foundational networking capability for the MakeRequest task, which fetches URL content in a blocking manner. The example uses it to demonstrate basic task execution within the graph structure, not for concurrent operations.
Hash define a typed dict to represent the state. Class state type dict. URLs list SDR. Result not required list SDR.
This type dict defines the graph state schema with required URLs, input, and optional result output. The mismatch with the returned results key follows the official LangGraph examples, where output keys often differ from the declared schema for demonstration simplicity. In production, you'd align these keys, but the pattern here focuses on showing the task decorator structure rather than strict schema enforcement.
At task, def make request URL, SDR, and make a request. Return requests, get URL text, 100.
The @task decorator wraps this HTTP request to make it checkpointable within the workflow graph, though actual recovery requires both persistent storage like SQLite Saver and explicit threaded reuse. This pattern demonstrates the basic structure for side effect operations in LangGraph, where each task becomes a node that can be individually tracked and potentially retried. The function truncates responses to 100 characters for demonstration, while the caller processes URLs sequentially via result blocking calls, despite the list comprehension structure.
Def call API state. Example node, that makes an API request. Requests equals make request URL for URL in state URLs. Results equals request, result for request in requests.
This node demonstrates LangGraph's task pattern, where each URL gets wrapped in an async task via MakeRequest. The list comprehension creates task objects, but immediate result calls force sequential execution, eliminating any parallelism benefit. The state schema mismatch, results, v's declared result, follows the official examples pattern where return keys don't strictly match the type dict. This is intentional for demonstration. With in-memory saver, state only persists for the current session, and actual recovery requires both SQLite Saver and explicit threaded reuse, neither shown here.
Return. Results.
This returns a dictionary with results, while the state typed dict declares a result field. The mismatch is intentional. LangGraph examples commonly use this pattern to demonstrate flexible state handling, where only typed dict declared fields persist between nodes. The actual state propagation depends on the declared schema, showing how LangGraph state management prioritizes explicit type definitions over runtime dictionary structure.
Hash create a state graph builder and add a node for the call API function. Builder equals state graph state. Builder, add node call API.
This creates the foundational LangGraph workflow structure using the basic task pattern. The state graph builder establishes a linear pipeline with call API as the sole processing node, demonstrating how to wrap side effect operations with the @task decorator for checkpointing capability. The example follows the official documentation's pattern of using in-memory saver for demonstration purposes only. This provides thread-isolated state tracking during the current session, but doesn't enable persistence or recovery across restarts. Note that while the list comprehension suggests parallelism, the immediate result calls actually execute requests sequentially in this simplified example.
Hash connect the start and end nodes to the call API node. Builder at edge start, call API. Builder at edge call API end.
These edges create a linear execution path through the single processing node. The first edge routes from the implicit start node to call API, establishing it as the workflow's only operation, while the second edge connects call API to end, ensuring clean termination. This demonstrates the minimal viable graph structure, a straight-through pipeline without branching, error handling, or actual parallelism.
Hash specify a checkpointer. Checkpointer equals in-memory saver.
This instantiates in-memory saver, a basic checkpointer that tracks execution state during the current runtime using thread identifiers. The pattern demonstrates structural checkpointing for stateful workflows, though this implementation only persists state in memory and requires explicit threaded reuse for any recovery. For actual durability across restarts, you'd replace this with SQLite saver or similar persistent storage.
Hash compile the graph with the checkpointer. Graph equals builder. Compile checkpointer equals checkpointer.
This compiles the workflow graph using in-memory saver for basic state tracking during execution. The checkpointer maintains thread-specific state via threaded, but only for the current session. It doesn't persist across restarts or enable actual recovery. This demonstrates the structural pattern for checkpointing, though production use requires a persistent saver like SQLite saver and explicit thread ID management for resumption.
Hash define a config with a thread ID. Threaded equals UUID. UUID 4. Config, configurable. Threaded, threaded.
Generates a unique thread identifier for state isolation in this demonstration. The configuration enables the in-memory checkpointer to track execution state for this specific run, following the standard pattern shown in LangGraph's official examples, where threaded distinguishes separate workflow instances. Note that this uses in-memory saver purely for demonstration. Actual persistence and recovery would require both SQLite saver and explicit threaded reuse across sessions.
Hash invoke the graph. Graph invoke URLs. https://www.example.com config.
This triggers the graph execution with a single URL input, demonstrating the basic task decorator pattern where make request operations become checkpointable. The in-memory storage maintains state only for the current session. Real durability requires both SQLite saver and explicit threaded reuse across invocations. Note the intentional state schema mismatch. While call API returns results, the state typed dict declares result singular. This follows the official examples pattern of simplified demonstrations, where structural clarity takes precedence over strict schema validation. LangGraph task decorator pattern. The @task decorator transforms blocking operations like API requests into checkpointable units, while StateGraph provides the structural framework for defining workflows with typed state and explicit start-end nodes. The list comprehension with result calls executes requests sequentially despite the parallel-looking syntax, and the state schema mismatch between declared result and returned results follows the official documentation's example patterns rather than representing an error condition. This demonstration shows the fundamental task decorator pattern for checkpointing side effect operations, though actual durable execution would require both persistent storage and explicit threaded management not shown in this structural example.
The checkpoint that remembers nothing preserves. Every thread